Hello, welcome to the first World CAAD PhD workshop. Today we are in the third day, and we will have 5 presentations and discussions about the topic material and fabrication studies and computational design. This session will be moderated by Virgo and me, David, and we are respectively presidents of CAAD and CAAD.
Sorry, I will cut you, but everyone is in their rooms, so I will pull them back now in 2 minutes, I think. Would that be okay? Ah, everyone's out. I'm just closing the rooms now.
Oh, so everybody was in the breaking rooms. Okay, break rooms.
Yeah.
I didn't realize that. Sorry about that.
No problem. They will close in 45 seconds.
And Koray, if you can send us or either on the chat room the schedule for today.
Yes, I will share it with you in a brief time. There are still people joining us now.
Good morning, everyone. I'm Paula.
Hello.
Hello.
Morning, Paula.
Good afternoon from us.
Yes.
Yeah, right. 7 a.m. here.
Hi, Paula.
Okay, now I stop the sharing and leave the mic to the moderators of the day.
Hello. We are all in the room. Yes, Koray?
Yes,
okay.
We are online and streaming.
Okay, and thank you so much. Okay, welcome to the third day of the first World CAAD PhD workshop. And today we will have a panel in the theme and the topic of material and fabrication studies in computational design. We will have 5 short presentations, and each panelist we will have 20 minutes for each work, and each presenter will have 3 minutes to short present or refresh his or her work. And this session today will be moderated by Virgo and me, David. Virgo is the president of CAAD and me from CAAD. And I wish you a very exciting session. And we will start with, Cora, if you can put in the screen, the structure of our session today is okay. Here are the moderators and the panelists: Tadeja Zupancic from CAAD, Paula Gomes from CAAD, Zaki Malazi from CAAD, Dorit Aviv from Acadia, and Anastasia Globa from CAAD. And the presenters, here you can see Yelda Jean from CAAD, and CAAD, Natalia Aquarius from, Yelda Jim is from University of Cambridge, and the panelists that will discuss the work will be from CAAD and CAAD. Natalia Aquarius is from Brazil, and she will discuss her work with panelists from Acadia and CAAD. And Emily Birch from Newcastle University. The panelists will be from CAAD and CAAD. The next, Nicoletta Carastati from UCL, Bartlett School, the panelists will be from CAAD and CAAD, and finally Islam Salem from the Ain Shams University, and the panelists will be from Acadia and CAAD. And we start with Birgul, that will moderate the two first presentations. Please, Birgul.
Okay, thank you, David. Yes, we have at our last day of the CAAD PhD workshop. So at the end, people have still have the same voting to state at the end of the day. So bear with us until the end, please, for all the audience as well. The people that are joining from the audience, just to inform you about that, at the end of the session, it will be a selection of the best presentation for today. That will last only 2 minutes, basically 2 to 3 minutes. And yeah, Koray, if you can send us the schedule, I'll put again first the actually now it's
Yes,
here.
Now putting it on the screen.
Tuesday, I have on my screen Wednesday. Yes, the first presentation presenter is for the University of Cambridge, Yelda Gin, with Emerging Earthen Architecture, Digital Design and Fabrication for Building with Earth. Yes, Yelda, you can take the words. I think you're...
She is not present here.
Oh.
I think we will pass Yelda, and maybe later on we will continue on her. We can go with Natalia Aquarius.
Okay, from Federal University of Santa Catarina.
Yes.
Is Natalia here? Yes.
Oh, I was a little bit, I was not prepared to start, but let's go. I will share my screen now.
Yeah.
It's everybody's seeing my screen.
Yes.
Yes.
Let me see. Sorry, my computer is I will start. I'm an architect from Brazil. I have a master in product design, and I'm doing my PhD in Federal University of Santa Catarina. I'm a researcher at LabCon, our environmental comfort laboratory. My dissertation, it's about optimal solutions for complex facade design with focus on strategies for solar control. Brazil, it's a warm country, and solar control strategies are an important concern in sustainable building design. The research is contextualized with the parametric thinking design process and with the mass customization context. It's the intention to discuss the intersection between the facade design, the analytical and optimization problem, and the parametric modeling strategies. First of all, I tried to understand the design problem, and I made some questions that at first impression maybe can be considered wide knowledge. For example, what is a window? What are the elements used in solutions for solar control in facades, and how do they work? And I started a literature review with these questions in my head, and to my surprise, I didn't see much material with this kind of general information. So I decided to collect them and construct the architectural design problem. This was available for the next steps that were the establishment of an interoperable and faster analytical model and modeling strategies for complex solutions considering glass and shading devices. The analytical model is based on the three-phase method, Braden's method. This is one of my taxonomies. The analytical model is based on the three-phase method from Braden's, and it is comparable with the architectural 3D model. I combined 5 performance indicators. 3 of those have a more quantitative approach. They are a metric for the light quality, thermal performance, and for ambient glare analysis. It is a novel approach to visualize glare analysis. And another 2 that have a more qualitative approach, they are shading device area and window obstruction. I'm testing meta-heuristic optimization models. They permit to understand the behavior of the design problem, but I'm preparing to test also some deterministic models. They might not have the capacity to draw the problem behavior, but maybe will give me faster answers. And I will include these 2 considerations in my dissertation. Now, my unified analytical model performs 10 times faster than the Daisy-based model that are my benchmark. I also produce grasshopper components as a result of modeling considerations. One of them is a simpler mathematical model to generate complex patterns for shading device in the entire facade. In previous research, limitation identified were the strategies to establish modeling parameters for complex shading devices and solutions for the entire building due to the mathematical problem, plus the complexities of the analytical models used. The pattern component permits to reduce the mathematical and because of that, improve the optimization process. Also permits to establish a cohesive aesthetical solution. It is possible to apply for any shading device solution and for the entire building, not just one ambient. My research was thoughtful, innovative architect from today, and because of that, the design background was taught in a didactic way. And this is my presentation. I'm really glad to be here in this group and curious about the questions. Thanks.
Okay, thank you, Natalie. So we have 2 reviewers that will review your research in depth from CAAD and CAAD. So I think we can start with CAAD representative.
Sure. Hi.
Yes.
Yes. Hi, Natalia. It's really great to see your work. I want to first commend you for the in-depth of your background and really starting from first principles rather than accepting conventions. I have one question that is quite technical about your equation. So DASIM uses daylight coefficients to reduce computational time. And I was wondering, does your equation use the same type of principle, or how do you actually achieve this increased efficiency?
Some researchers use some complex models to analyze, and they use the same models to do optimization. But in this time of the design process, we don't need to use really complex method to simulate. And I started to study methods to analyze. I tested a lot of tools, and I finished with this method that is Braden's, that is the 2-phase method. It's a simpler method than the DASIM method. The DASIM method, it's a really good method, but it's a good method to analyze design in the advanced stages of design. We need to. It was a concern. How can I say? The mathematical result, the accuracy. It was a concern, but we need, in this step, we need to do a balance between the velocity and the accuracy. And I made a lot of tests. I published a paper about that, about how we can validate a tool for the design step. And because in design step, we need to classify solutions to answer some questions. We don't need to have a high accuracy numbers because we don't have the all design. Or I don't know if I.
So yeah. So do you basically not use such a complex sky model? Do you use just direct and diffuse, or how do you? Yeah, maybe you can just explain exactly how you reduce the complexity of the model.
Okay. At first I didn't simulate all the year. I simulated representative data that represents all the year. The method, it's more faster. It's a more fast, natural, more faster method. And I use it only one method to do all the analysis. Some previous research used more than one tool to analyze thermal performance, for example. And I did method that use only one step to do all the simulations. Have a lot of other considerations, but at now the most important was these two considerations: the method and the simulation method, and the data that I use it to choose how can I will represent all the year in the simulation.
Okay, yeah. So I'm just going to then make a final comment, which is, first of all, you answered already my question that you already validated your model, right? You have a paper about validation. And the second thing is, I think it's maybe just important to emphasize that your simulations are really geared towards the concept design stage or the early design stage, right? Because you're looking really into simplifying the model to give faster results for multiple iterations, where if you want in a later design stage to really get accurate conditions of the room, you may want to go to other models. So yeah, I think it's definitely a great contribution, because we all get stuck simulating daylighting for hours. So congratulations on what you have achieved so far, and I'm looking forward to see more.
Thanks. I will. It will be a consideration. It's really, it will be a consideration. It's a thing that I'm thinking about a long time, because when I started to simulate, I was thinking that it's not can be this difficult for architects, and it is a thought for me. Thank you for the comments.
Okay, so our second reviewer will be from ASCAD.
Hello, good morning and good afternoon. Thank you, Natalia, for such an excellent and complete presentation of your research work. I really especially found the clarity of visuals, the narration and the presentation content kind of very informative. I do have 3 questions, so I'm going to go one after another. Hopefully the time will allow me. My first question is regarding such important keyword that you're using in your thesis title, control of insulation. I'm a little bit confused because I did not have or see any further discussion or reference to the insulation control that it relates much to thermal performance. This is a question in the style of an inquiry. If you would like to help in the answer, because I didn't find any reference to the word insulation.
Yeah, to contextualize, I live in a really warm city, and it is known as a city of sun.
Okay.
And here we always need to protect the sun. And when I made my title, I think about in one word that represents the sun. I don't know if it's the best yet.
Yeah, great. I mean, it's up to you to title the...
I'm accepting suggestions because for me, titles is so hard to do.
Yeah, I got from a different perspective. I thought, control of thermal performance and daylighting. Very straight, simple, and the reader can relate to it. It's up to you to, as an author and a researcher, to modify it, but this is just an inquiry. Thank you for your answer on this. My second question is can you verify how you assign different priorities or weighting system in your multi-objective function to say as a criticality measurement? For example, are you giving more priority to the daylighting values more than the thermal or heat load transfer? Are you using any criticality or different priorities in your multi-objective function?
I use it multi-object function, and the mathematic methods permits to understand the behavior of the problem, and they find a frontier of the problem. Mm-hmm. They answer for us a lot of possibilities, and we can choose these possibilities in this frontier. This frontier represents the best relations between the parameters. But if daylight is more important for the design, I can choose some solution in this part of the frontier. And I also can classify the solutions using the qualitative indicators also, and I can also include another one if you be an interest for the design team.
Thank you. I think that really clarifies my question. I would expect that this is like the previous panels mentioned, this is a conceptual design tool. Perhaps me as a designer, as a user, I want to focus more on the daylighting values, or maybe more on the shading device shape and size for economical construction. So it would be good to have flexibility in such priorities. My last question is, how do you evaluate your research output? Is it via a case study comparison, a real life case study, an end user evaluation, or produce a guide and index for the best methods for facade performance design criteria? Tell us a little bit more about how you're going to validate and evaluate your outcome.
I'm thinking a lot about that, and I'm preparing to start a sensibility analysis to answer how optimized are the solution. And then I'm also will compare the results in the frontier with the highly validated simulation methods to validate the results, and also to validate the to answer if the method it's a good method to do optimization. Is the two stages that I'm preparing for validate my research.
I think this is a very interesting research area. Definitely the practice and the research has to merge together and have facility of tools that help them address these challenges. It's a really great presentation, and thank you for addressing the questions, and thank you so much.
I appreciate all the comments. I'm really happy to be here, and really thank you. Thank you for the comments for the both of panelists. Thank you.
Thank you, Zaki. I think we have a couple minutes to 3 more minutes to take questions from our other panelists and as well as from our audience that are following us through YouTube. Please be free to write down your questions, and Koray will post them on our chat window. So we will ask your questions to you, Natalia. So first, our other panelists, do you have any comments, critics about the work? I have to include to see all the panelists in the gallery view because otherwise I don't see them all. Okay. So one thing that before we move to the Yelda's presentation, one comment that's what I found your presentation when I was reading it and when you were preparing presenting as well, maybe to mention that this kind of research fits actually to the state-of-the-art research that are involved basically to reduce the carbon footprint of the construction industry. So it has a value really into that, all this solar analysis, because a bigger scale, if you look at from the bigger scale, how does it contribute to the construction industry and the design world, which as designers, I mean, architects and construction businesses are really polluting a lot word now. So I think your research and the outcome will have a good benefit in terms of reducing the carbon footprint if it's developed well. So that will be my just comment before we switch to Yelda. Thank you, Natalie.
Thank you very much.
So our first presenter was Yelda, but she had some problem with connecting through internet. Now she is in. So I will give word to, she's in, yes, I can see her, yes. She is, I'll give you words, Yelda, for your presentation. She's from the University of Cambridge.
First of all, apologies for being late. For 10 minutes, I had an issue with my connection, as Birgit said. Before sharing my screen, first, I would like to thank all the sister CAAD organizations for giving us this very rare opportunity to meet with all of you and all the panelists. I really appreciate it. And also special thanks to Birgit, Koray, and the team at Istanbul Technical University for their effort and making this happen. I will start my presentation. I try to limit it to 3 minutes to be fair, which is very hard to explain everything in 3 minutes. I hope the audience had the chance to have a look at the video online. Let me share my screen now. I hope you see it well.
Yes, we can follow it.
Okay, excellent. Right. I'm a PhD candidate at the Center for Natural Material Innovation in the Department of Architecture at the University of Cambridge. The title of my research is Emerging Earthen Architecture, Digital Design and Fabrication for Building with Earth. My supervisor is Dr. Michael Ramage. So during this short presentation, I'll try to explain you why I do this research and what's the significance and impact is, and what my objective is, and how I aim to achieve that objective in terms of process and methodology. So why does this research matter? Because construction industry is responsible for 40% of the energy and process-related carbon dioxide emissions, and 11% of those emissions were caused by manufacturing building materials like cement, steel, and glass. With the growing population, 40 billion square meters of construction demand is estimated for the next 20 years. And the rising demand in construction is widely supplied by conventional concrete and steel buildings, worsening the impact of the construction industry on the environment. So using local, reusable, and sustainable materials for construction, such as earth, presents a great alternative for an environmentally sustainable future of architecture and construction. So earthen building techniques have been known for more than 9,000 years, yet in the 20th century, earth lost its popularity to industrialized materials like concrete and started to be acknowledged as a primitive material. There are several vernacular methods of building with earth, as you see on this image, which some of which I had the chance to experience firsthand. Earth has many benefits, actually. It's a reusable, available, worldwide material. It's also affordable, energy efficient, low carbon, non-toxic, non-polluting, and requires no industrial processing. It also creates healthy and pleasant indoor environments by balancing the humidity and storing heat due to its thermal mass. So one asks himself or herself, so why is earth not widely preferred as a construction material if it's so beneficial? What are the challenges? Well, earth shows different characteristics based on the location of excavation. It's not a standardized material like concrete or steel. It's not water resistant, needs to be protected. It requires periodic repair, and unstabilized soil has low compressive and tensile strength. Earthen construction is also labor intensive and slow, especially for developed countries. Regulations to construct with earth is limited around the world, unfortunately, and it's also very hard to find experienced constructors or trained engineers in this field. So lately, there have been several attempts recently to mitigate these challenges and to make earth a more mainstream material. One example is prefabricating rammed earth wall units by Martin Raj, as you see on top left. And another example is CAAD, which is an international research project led by the universities in France and the UK. And it aims to develop a novel low-carbon cope building technology that enhances cope building technique structurally and climatically, and hopefully this technique will also have a place in regulations. So what is the future of earthen architecture? What can be the future of earthen architecture? During recent years, there has been a growing interest in understanding material behavior and researching ways of enhancing the use of the material in architecture with computational design and digital fabrication. Additive manufacturing is enabling us to create complex forms which could not be realized by conventional ways, and by placing the material exactly where it's needed with precision, it is now possible to increase the structural and thermal efficiency of building elements and also avoid material waste. Here we see precedents of on-site additive manufacturing. On-site additive manufacturing with earth has several benefits. Earth has an advantage for regions where wood and concrete are expensive and require long-distance transport. This process does not need scaffolding, hence is largely waste-free. Positive qualities of an earthen building, such as thermal regulation, can be enhanced, while the disadvantages, such as labor-intensive construction and structural weaknesses, can be eliminated by combining these technological advancements. This advanced process also gives the architect the ability to quickly test the performance of a building element, providing precision during fabrication and allowing optimization through multiple prototypes. Another benefit is the plasticity of earth makes it an easily customized material. It's now possible to control the performance of the fabrication process with simultaneous feedback from sensors and robots. The behavior and performance of earth during the fabrication and life cycle of a building can be tested and documented more easily, making it a more predictable material to work with and accelerating its use as a mainstream construction material. Moreover, the automation of earthen construction can provide fast and efficient construction for developed countries. So my research aims to contribute to this field and its adaptation to the industry. There are three main research questions that I will try to address with my research. I have just finished my first year recently in my research, and it's going to be 3 or 4 years. How can we enhance conventional design and manual construction of earthen buildings with computational design, additive manufacturing, and automated construction? This is more like an umbrella question, as you can see. And the second is, by using material-based design computation, can we improve the structural and thermal qualities of earthen buildings and develop a 3D printable spatial design vocabulary to create a variety of building programs, which can also be customized? And the last one, how can on-site additive manufacturing with earth can reach a wider audience as local, collaborative, affordable, and low-carbon construction process? And as you see,
we have to sum up, Yelda, because we're using 7 minutes, so you have eaten your discussion time.
Okay, then I'm not going to get into detail.
Yes, please.
Perhaps the audience can read about my methodology. I'm just going to talk about this triangle you see there. At the heart of my research is material behavior, which I find very important for this research. And the other edges of the triangle will be earth mixes, additive manufacturing, and material-based design computation. There will be several experimenting with earth mixes, form finding, and prototyping. And I aim to do a real-life prototype at the end of my research. Thanks a lot for listening. I was going to get more into methodology, but that could be more as answers to questions. Thank you.
Okay, thank you. So we have just left time for the panelists' questions, but not for discussion. It will depend how we pursue with the panelists' questions. So we have 2 panelists from Kadria and let me check, and Sigradi. So Kadria, I think Candy Christine Herr, is it?
Or I think Anastasia is joining.
Anastasia, I'm sorry. Yeah, then I don't have those names here. Is Anastasia here from Kadria? Yes.
Yes, I'm here.
Great. So we can have your comments.
I'll probably sit this one out because I joined just midway, so I'll jump in starting from the next presenter.
Okay. So Sigradi, the representative of,
I think, right. Hola. So, yeah. Well, thank you for your presentation, Yelda. I have a couple of questions, actually, about. Okay, so you mentioned that one of your goals was material behavior for finding, prototyping, and looking into how to adapt these methods to industry. First of all, I think it's very interesting and true that this is carbon emission, like zero carbon emission. And there is a lot of research in the NASA program for similar approaches with Martian soil. So one of my questions to you is that if you are planning to look into different type of soils, because depending on the region that you're looking into, probably the soil has different material properties. And if there is any characterization of those type of materials properties, if maybe you can expand here on your methodology on how do you plan to work on this material analytics for form finding.
Thank you, Paula. That's a very relevant question, and I thank you for that. In fact, that's one of the main questions I'm asking to myself too, and that's one of the main problems why earth is not a standardized material worldwide, because unlike concrete, everywhere you go, earth is different. Like even in the same country, if you go to another city, the earth quality is different. So when you build with earth, you need to send the earth to lab to get a lot of tests, and then once you get the result, you start building with it. So in terms of that, I think I have 2 options in front of me. I will either localize this research and say that I am focused on the earth of this region, and I get the results from the lab and work on that with my earth mixes, which is very important because I will need to test the printability of my earth mixes unlike conventional materials. And the other way could be setting performance requirements for Earth, let's say in terms of climate, in terms of structure, and then as a worldwide sort of performance, let's say, guidance, or even a booklet, something like that, I can sort of say that like the performance of printable Earth mixes should reach this criteria, then allow the users to sort of make their own mixes to come up with that, like sort of a benchmark, if it makes sense.
Yeah, it does. Thank you. Are you thinking also on including extra different fibers to make it like high performance type of
yeah
structures? Okay.
Yeah, definitely we need like additions, because as I said, like Earth performs well under compression but not so well under tensile strength, so we definitely need reinforcement, but I will try to look for natural reinforcement such as like straw, organic materials, rice husk, because like the main goal is to mitigate our effect on the environment. So I don't want to use anything that requires industrial processing. So these will be the things that I'll look for. I will also need to include stabilizers. And for that, like the usual practice is using cement for earth stabilizing. But I will try to avoid it, or maybe keep it up to 5% max to still make this like really sustainable instead of greenwashing. Thanks.
Yeah, thank you. I really recommend that you look into the NASA research in Mars 3D printing, because they are also carbon negative, some of the materials, so actually subtract carbon from.
Yeah, thanks a lot. I actually looked into their research a bit because, you know, the main reason they won't be able to carry material from here, so they're gonna use the material over there. So yeah, it is quite similar, because I want to do an on-site additive manufacturing as well. So,
they call it in situ resource utilization.
Yeah, exactly. Thank you.
Yeah, thank you. Great presentation.
Thank you.
Okay.
Maybe I can have a question on behalf of Kadria.
Sure.
Yes,
all right. Thank you, Yela, for your work. I'm aware of the work of your lab already for some time. You're doing great work on bamboo and also on earth, and that's really impressive. In China, people are really watching what you're doing, because we have this big question: what to do with traditional materials and how to reuse them. And so my question is about all the advantages of earth and earth structures, earth-based materials. Normally, we really think they're low carbon and kind of very environmental friendly, because they can be produced on site, but also because they can be fabricated using manual labor and traditional skills. Now, you're proposing, however, to introduce that in a context of digital fabrication. Now, that negates some of the advantages that this way of producing earth-based architecture has. So you need, accessibility by robots, you need the robots, you need, lots of equipment. Do you factor that into the claim that this is still a very kind of low energy, low carbon building material?
Thank you, Kenneth. That is a very relevant question indeed. And I'm also directing that question to myself a lot, and I get it a lot from people. So first of all, I'm aware like how precious it is, the earth for developing countries. Like, for example, Rwanda Cricket Stadium is a project done by the practice of my advisor at my research group. And basically what they did is like they utilized the local material with local workforce. They basically just taught people how to work with thin tile vaulting. So they increased the economic let's say sustainability of the local environment by doing that. So like there is this very, very nice quality about earth, about the labor it brings to the process. So I totally respect that, and I think it should stay like that. My proposal is more for actually the future of architecture. I think it goes like two ways. Like first, I think automation in architecture, I think, is inevitable. I don't think it's the choice we make. It's something that will expose on us. And if we're not ready for it, let's say in 5 to 10 years, I don't think we will be decision makers anymore. So in a way that like this is kind of preparing ourselves for that future. That is one aspect of it. The other aspect of it, like for developed countries, unfortunately, earth is not preferred for the very reason it's because labor intensive. Like it's also because like we don't see many earthen buildings in Europe or Northern America because people know they will need to hire a lot of people, they will need to wait a lot for earth to dry, so and so forth. And obviously regulations, unfortunately, doesn't allow us to build with earth either. That's another aspect. But yeah, for the developed world, I think like decreasing the labor need will help making earth as a mainstream material. And also for the near future, maybe in 5 to 10 years, I think we will see this. And currently, yes, robotics and automation is very alienating, very not common for all the industry. So I think we should also look into ways to make it more affordable, as Ryle and Sanfratello did, like they created their own robots for 20% of the cost that you find if you go buy it, or like making let's say a very sort of approachable software for people to use it as well, because it's, as you know, very complicated to use these systems as well. So I think these are the measures we should take to make it more approachable and democratize, I believe.
Thank you so much, Yelda.
Thank you.
Okay, thank you, Yelda. And we will now turn to our audience, to other panelists. If we have time for 1 or 2 more questions. We have to contribute. I have to put.
Maybe I'll ask a question.
Yes, please.
Hi, Yelda. This is Kathy Velikov from Acadia. Really exciting work. I'm excited about the future of Earth architecture. You mentioned this briefly, which is the regulatory environment around new materials, and I wonder if I know that it's not your central focus, but if part of the research is aimed at trying to change building practices and what's acceptable as building materials and our kind of material and manufacturing environment. I wonder if there's a part of the research that can look at the regulatory environment, and in many ways that's also a kind of hyper-local condition, just like Earth, and so I think the locality of your of where where the research where the work or where Earth architecture is possible, and then where there's a regulatory environment might be part of this kind of matrix of possibility that perhaps the work can kind of address.
Yes, thanks, Kathy. Another very relevant question, and I'm gonna do that as a subchapter in my PhD because it's very important. Because like I really want this to be adopted by construction industry. I don't want this to be left on paper. Hopefully, so yeah. I mean, there are so many efforts worldwide on making Earth involved in regulations. Like recently, I just joined an Earth and building conference, and I listened to this organization, and they have a web page called Code.org. If people are interested, they're trying to actually put Earth on regulations in states around California. And like he explained the process, and it took them almost 10 years basically to be as a group, come up with this group with ideas, with engineers and architects, and do the tests and do the policy work and convince the people who it is like so diligent, to make these things happen. And it kind of breaks my heart because it shouldn't be this hard when you're trying to do something good for the planet and for architecture. It really puzzles me why it's so easy to build with concrete and you have to go through all these hindrances when you want to build with like earth or timber. It really should be the other way around. So I think more than architects, policymakers and people should really pressure policymakers to make these changes. Like there should be a demand, like people should demand earth and architecture, timber architecture for these things to happen. Because as you know, there is only so much we can do as architects, and like I will definitely talk about these issues in my report. And then I think like very good efforts are being done in New Zealand as an example of like regulations of earth, in Australia, in certain parts of states, or in South Africa. But yeah, I mean, there is not a worldwide standard like that would really change things if there was one. Hopefully there will be, but we need policy change. We need like carbon taxes for these things to happen. And I look forward to seeing them soon, hopefully. Okay,
yeah, thank you very much. Very exciting research. I'm quite sure that we will have a lot of discussions in near future about these new materials and how we are going to save our world, because architecture really plays important role in that, in construction industry as well. As that, I will now switch to give the word to David for our next three presenters.
Thanks to everyone.
Thanks, Birgul. And then we go forward to the next presentation from Emily Birch from Newcastle University. Her work is Hub for Biotechnology in the Built Environment, Bees, Subtils, Spores, Hygromorphs as a Novel Smart Material. Please.
Yeah, thank you. Is it all right if I share my screen? Can you see that?
Yes, perfectly.
Brilliant. As I say, thank you so much for inviting me here today to present my project, Bee Subtilis Spore Hygromorphs as a Novel Smart Biomaterial. I'm Emily Birch, and I'm going to use my poster as my background for my presentation. So we have a global energy crisis. Currently, buildings are using 40% of our global CO2 emissions, which I was touched on in the last presentation. And a lot of this is actually coming from controlling relative humidity within the built environment, as we currently don't have any passive systems for regulating that. So what I'm trying to do is look and see if smart materials could hold the solution. So actually, there is a class of smart materials called hygromorphs, which are a naturally occurring smart material which responds directly to relative humidity, which is perfect. They achieve this by utilizing the molecular energy released during evaporation. So on an architectural scale, it's passive, but it still uses that energy. There are some examples which you might be familiar with, such as the pine cone or wood, but the one I'm going to be focusing on today is the bacillus spore. And that's because it has a specific structure which gives it advantages for the architectural environment, which the others don't hold. So the bacillus spore is specifically designed to survive for thousands of years in the environment without degrading. And its internal structure allows it to expand and contract by 12% in response to humidity, which is actually a quite significant amount for a hygromorphic material. So what we've been doing is utilizing laboratory techniques to both grow and sporulate these bacteria. And then what we're really trying to do here is maximize the hygromorphic output of these spores. So by changing the culture conditions slightly to optimize the hygromorph. So now we've got these hygromorphic bacteria and spores, we want to control them. We want to know how we can use them to our advantage. And so to do this, we've been applying them in a bilayer structure, which you can see at the center at the bottom. These are some initial prototypes. And that bottom image shows a spectrum of responses at the same humidity. So what this has shown us is the initial results from this is that it's rapid and repeatable. So we can get this shape change over many cycles in a matter of seconds. It's also programmable. And really importantly for this is it's got a significant force output, which we'll be touching on later. So now we have got a bit more control. We want to amplify it. We want to say, how can we use this to our benefit on an architectural towards scale? So what we're using plant biomechanics and an understanding of the form and function of the specific tissue architectures of plants, which use a singular cellular expansion, which is representative of the spores response, to then instigate a larger response on a larger scale. So such like the Venus flytrap uses that single cellular expansion to open and close its traps. It gives us a a biomimetic approach for how we can scale this up. So the next step is, how do we bring these things together? How do we utilize that hygromorphic response with these tissue architectures to produce something useful? So we're going to be beginning to use digital fabrication techniques to do this. So we're investigating materials and forms which can be printed to combine and mimic the plant architectures with the hygromorphic motion, which brings me to my aim. So the aim for this is to produce a showcase dynamic creature or organism using the bacterial spore hygromorphs as the motion and the plant biomechanics to amplify, and then 4D fabrication techniques to realize it in the physical world. So how do we do this? Where next? Well, while the observations of the plant studies have and of the spores have been effective, CAAD can really take our understanding further. So we can take that knowledge of the plant tissue architectures and apply things like 3D scanning to give us a further visualization of these structures on a digital platform. And then we can use things like generative design to realize these structures in a digital form, whilst also inputting the knowledge of the bacterial spores force output to give us something which can combine these things together into one organism as such. So CAAD really kind of becomes my archaeologist, my architect, and my engineer all in one go on how to evolve this creature as such. So the aspirational outcomes for this project is to produce the material palettes which can demonstrate the properties of this new smart material and the capabilities of it, whilst also providing a technical and design foundation for people to take this material further on towards the architectural scale and architectural applications, as it's very much in its infancy at the minute. And the aim is to produce a spectacle creature which can bring all of these things together and produce a playful interaction between the user and the building, and highlight how you as the user impact on that space and give it a visualization. And hopefully this will challenge the awareness, range awareness, and challenge the preconceptions that we have about our impact on the built environment. So hopefully we can capture the interest and the fundamental understanding that people at, say, the grassroots level, beginning on a bottom-up approach.
Emily, sorry. Yeah. I ask you if you can go to conclude, because we are compressing the time for discussion, please.
Sorry, this is my last sentence. So sort of beginning on a bottom-up approach to raise that awareness and hopefully get these biomaterials more accepted within built environment. Thank you very much.
Thank you, Emily, so much for this fantastic presentation. I asked to Anastasia Globa, that is the first panelist, to question and discuss with you, please.
Thank you for the presentation. That was really nicely delivered. Although in architecture, we usually have so many slides that a person talking to one panel is quite refreshing. So I had to use my imagination, which is all right. So my question is, although it's very exciting, and I'm kind of imagining lots of applications, and you're sort of empowering or the groundwork for people then to carry into the design practice, right? But if I was looking into that and was thinking to play with it or try to apply it in architectural scale, I want to know, for this new material, what would be the structural qualities? Is it load bearing? Would it be brittle? Would the dust start accumulating in it, so you have to have a composite material like covering it? So just if you walk me through all those very important kind of considerations, that would be great.
Yeah, absolutely. And this is something I'm working on at the minute. The material itself takes its qualities from the substrate you apply it to, because it's obviously, you have to form it in a bilayer. So the spores themselves are very much, although their function is primary, they're secondary to the material's structure as such. It very much takes the form. So those initial studies you saw there were done with latex. So if you imagine it's very tactile, it's got a lot of movement in it, it's soft to the touch. And the work I'm starting to work with now is flexible 3D printable materials. So it's a plastic-esque material, and I'm trying to work more towards using a biological material as that base. It is a soft material. it wouldn't be the sort of thing I would be recommending to go on an external side of the building because of that fact that it needs to be flexible. This is why at the start I'm working towards more of a material palette so people can understand what it can do and where we can push it towards. In some of the initial studies, I was working towards a soft origami structure, if that gives you a bit of an idea of what it feels like. Yeah, so I hope that answers the question.
Yeah, thank you. Yes, it does.
Thanks, Emily, and Anastasia as well. Please, Paula Gomes from Sigradi.
Yeah, thank you, David.
Okay.
Well, thank you, Emily, for your presentation. It's very inspiring. If I understood correctly, you are using the exact material and it's not a biomimetic application, correct?
I'm sort of using a multi-pronged approach. So I'm using the actual biology from the spores, and then I'm using a biomimetic approach from what I can learn from the plant kingdom. So I'm coming at it.
So both combined. Okay. Yeah. So my question would be in either case, what are the constraints that you see for this material, and what are the, we saw the pros, and what are the cons? That's my question around, like, what is the, for example, the range of humidity that you can work with, and what does it imply for the application?
So those examples I showed you there, they were all responding at 42% relative humidity. I've tested them down to 5% relative humidity because that is the lowest I can get. And that is where you achieve your maximum shape change. Maximum deformation is at your lower end, and your maximum relaxation is at your upper end. So I've tested from 5% to 95%, and you see a response throughout that entire spectrum. The reason why I tested at 42% was because that was my room humidity, and I wanted to see how it interacted in a real setting. As far as the limitations of the material, obviously, because of the substrate we're working with, and it is a biological material, it has the fact that it is, although the individual spores themselves are robust, the material you're applying it to isn't necessarily as robust because it's a flexible material. We have certain issues with how do you turn this material on or off, because obviously it's a biological material. This is something that I don't think I will have a chance to brush on myself, but how do you plan in a stop in a biological system? So if you say had this on something that opened or closed and building membrane, if you didn't want it to do that, how do you stop it? Things like you could use a mechanical stop, or you could maybe build something in synthetically into the genome of the bacteria. But I'm not a biologist, so I couldn't suggest those right now. But yeah, there are a few we could go into. They're the ones I find most interesting myself, but yeah.
Okay, yeah, that's great, thank you. So from there, from the limitations, do you see any opportunities from the limitations, not from the advantages?
So for me, the interest is in the material itself, although the biology side is really important to me. I'm not a biologist, and I don't want to start trying to train as a biologist when really I'm an architect at heart. So as much as I take inspiration from it, my interest is in the material. So what I'm trying to do now is see what range of materials I can work with, from fabrics like silks and knits and things like that, all the way through to using like metal alloys and very thin films, and seeing what response I can get out of those materials, and how I could maybe produce a more robust material which still has those flexible elements in, by using things like 4D printing, which could use etching within a material to allow movement without using weakness of material, and that side of things. So that's where I think the opportunities come from, those limits, and I'm quite excited to see where that goes.
Yeah, that's great. So in that sense, when you have all these variables, what do you see as an outcome from the research itself beyond the, this structure that you are planning to create, right?
Yeah, so my goal is, I'm doing a creative practice PhD. So for me, I'm really hoping to put together an exhibition of such. And within that exhibition, I really want to, my goal is to showcase the range of responses this material can have with relation to the human and the building. I want it to be able to make people think about, okay, when I turn the kettle on, it increases the humidity in this space, and therefore I have a visual representation of what that does through the movement and the shape change of my creature. And I want to be able to sort of challenge that preconception about the fact that we use a building and that a building doesn't use us, and break that boundary down. And, you know, as was touched on in the last presentation, you know, I really hope we can challenge why are we not breaking through this boundary of we can give back to the environment instead of just take away. And hopefully this movement that I can create through this will provide a visualization of that, whilst also providing a material palette to take forward with a specific application in future.
Yeah, great. Exactly. That was my question. Thank you very much.
Thanks, Emily and Paula as well. We have some more minutes. Before I open to the other panelists for discussion, I warmly invite the YouTube audience, if you want to know more about the works here, you could chat, and then we can transmit here for the presenters. And please, if you have questions here, or the other panelists and presenters, feel free.
I have a question to Emily.
Okay.
First of all, thank you. So first of all, very inspiring to see the breadth of your work and the methodology being so rigorous. I really enjoyed watching your full presentation on Vimeo. But you started by saying something that I think, you know, should be reconsidered, which is we're not able to do this with manufactured materials. And actually, I've been working with hydrogel for a few years. And that's a material that is chemically made rather than biologically, and expands and contracts with changes to humidity, basically. And also has the ability, you can tune it to transform from hydrophobic to hydrophilic, etc. Right? So it has some of those mechanisms that you're working with. That, and I mean, this is only to say that I'm interested in the comparison between them and how, you know, what are the efficiencies or what are the things that you can achieve with the biological response rather than the chemical response? Because, you know, I found what you're doing very inspiring, and you know, as someone that works with humidity a lot, I really, you know, I'm really impressed by it. But I just want to know more about you know, different techniques to achieve this and how they differ from it.
I'm really glad you've asked that. I'm actually familiar with your work, and when I saw you were on the panel, I was almost certain you were going to ask me this question. Because I was trying to keep to time, I didn't go into what I was meaning there. And what I was meaning there is specifically for application to the architectural environment due to its resilience. So because the bacterial spore, its specific makeup is designed to let it last for thousands of years. It can be, you know, sent out to the moon. It can be harvested from glaciers. It's very robust to the architectural environment. And also it doesn't sort of get contaminated as such. So I know things like hydrogels can get contaminated quite easily. You know, they almost have agar-like properties, and they are not as robust as a spore. That's what I was referring to there about we've not been able to achieve in the synthetic world yet, is something as robust, but also as effective. And that's where I think there's potential advantages to using the spores. You know, initially I was looking at hydrogels and things like that. I've also looked at, so there's the specific protein within the spore, which is peptidoglycan. Looked at maybe we extract that out of the spore and we use it in a synthetically reproduced way, but actually when you do that, you lose the properties which the spores give. So the spores themselves, they have a specific coat morphology on the outside, and it actually zips together with the spores around it, forming a very tight monolayer. which actually helps in that hygromorphic response because it means everything pulls together and you don't end up with things like cracking or degradation of that surface. So there are quite a few benefits to using these bacterial spores over things such as hydrogels. So yeah, that's why I was quite excited about using them, and I think it would be lovely for us to have a conversation maybe without monopolizing this, but I think we could really get something good.
Great, I think that's a great answer. Just talking about the robustness, and because the hydrogel also undergoes degradation after after a number of cycles. So thank you.
No worries.
Thanks, Emily and Dorit. I have one question that is connected with the Doris. Which is the life cycle of the life period of this bacteria, and how to improve this lifetime?
So the bacteria itself has a replication cycle very similar to E. coli. So every half an hour it will reproduce whilst it's as a live bacteria. But what I've been working on here is if you limit the nutrients in a certain way, the bacteria almost forms its own sort of seed, which is the spore. So it's a very limited life form, I guess, of the bacteria. It's not genetically active. All it does is maintain the DNA, which is actually why it's hygromorphic. So that's its way of protecting its DNA core over thousands of years. It genuinely is thousands of years. It can go through millions of cycles of expansion and contraction in response to humidity without showing any response. Obviously, that's not my work. People like Chen et al. Have done lots of studies into the robustness of these bacteria spores. There are also different bacterial spores we could be using, but B. subtilis is the easiest to work with, and they hold themselves the best in the monolayer. As I was saying to Dorit about that zip structure, they do that incredibly well. So it's a toss-up between hygromorphic response and resilience, which is why I've chosen that specific spore.
Thanks, Emily, for the response and sharing for your fantastic research. We need to move on to the next presenter, that is Nicoletta Carastati from UCL Bartlett School of Architecture. Her work is how the process of knitting and material programmability can inform the design and fabrication of highly specified sustainable architectural structures. Welcome, Nicoletta.
Perfect. Hi, it's great to be here. I'll just share my screen. 1 second. Share. And you can see, right?
Right.
Perfect. Yeah. Okay. So I'm Nicoletta from UCL the Bartlett. I'm very happy to be here around you, and I'll take you through very briefly my process. So the current question is how the process of knitting and material programmability can inform the design and fabrication of highly specified assemblies. And the work currently sits at the intersection of 4 components. So we have architecture, textile, material science, and finally computation. And now let me take you through that kind of 4-step approach that I'm aiming to be exploring. So the first one includes of understanding the materiality and the making of the yarn. The second one includes the design and the knitting pattern, and also the design of the various knitting methods that could be applied. Moving on to the third stage, which is the assembly of the form within the space. And finally, the fourth part, the 4th dimension, is looking at examining of the relationship of the assembly and what relationship it has with the surrounding environment. And to do so, I'm planning to explore 3 different kinds of methods in parallel, looking into material programmability, knitting programmability, and how these can be informed, and also inform the digital simulation. So what is the relationship that can happen there? And I'll show you briefly kind of old examples of work to see. So this one was an early knitted prototype that was exploring and actually learning how to knit and use knitting patterns and different material consistencies that was made out of natural products such as wool and cotton. Moving towards more recent kind of exploration of actually extruding hydrogels into yarn formats, in which you can, as actually mentioned, you can tune into specific properties, and that one had also different consistency of algae that gives the different color that, as you can see here, in some parts is alive, in some other parts is not. And the third part is examples of, again, very early stage of digital simulations, which I aim to use in 3 different ways in the research. So one would be to actually design the structure or the product. The second one would be from that design to derive the knitting pattern, and the knitting pattern can then be translated or put into a high-end knitting machine that can produce complex structures. And then finally, also through these simulations, actually exploring the relationship that the textile or the assembly might have with predefined stimuli. So depending on the properties and the tuning of the materials themselves, how does it respond to the environment or to moisture? And to end with, actually it's a diagram, but it's looking at, it's a more of an overarching concept. And what you can see here actually is the cross-section of a human body and its relationship with the surrounding layers. So what I would like at the end, hopefully, to explore or to have is to look at those different layers that surround us, and effectively actually the third skin, the third layer, or the envelope. And what is the relationship of the body, the envelope, and the environment. And hopefully that would be done through a large scale or larger scale prototype. And that's me. Hopefully.
Wow, thanks. Perfect. 3 minutes straight. Okay.
Really? Well,
yeah.
try.
Yeah. Okay. And Tadeja, please.
Yeah, thank you. Thank you, Nicoletta, for your ambitious description. I would say, yeah. And I wonder how you see your strategy through your research path in relation to the unpredictability you can imagine, and maybe even risk management. And I wonder from 2 aspects. One is the scalability of everything. The other is you have hyper-defined structures, but what about a hyper undefined environmental conditions? Because when I was reading your text, at the end I asked myself, okay, but this is probably, again, this lab-based prototyping. What about this uncontrolled environment, and how can you make your experiments relevant for this kind of unpredictability?
I think that is a very good question. And to start with, the scale is always something very challenging at this part. And I really would love to see if there are ways of scaling up, because either by even potentially even scaling up a machine or scaling up the fabrication methods, or using different fabrication methods or different extrusion thicknesses, that I can see how I can really kind of scale up to a specific point, obviously. Now, in terms of how it will respond to the environment, I think up to a point, I am quite curious to see if I were to test it, and I want to test it like externally, how would it degrade how would it respond to the environmental conditions? And I want to see how can I make that part of the design. So what is the kind of building up for that tolerance, or seeing, can I have a specific tolerance? I can say, okay, up to this point, it's acceptable to have it within the design principles, and it's kind of the behavior of the material itself. And I don't know if that was kind of clear, or...
Yeah, maybe you can continue with this idea of what is acceptable. How will you decide about what is
acceptable? I think my current problem is because I'm in the very, very beginning. So I'm actually on my first month of a part-time PhD. So I think I really need to concentrate and really identify what are the key things that I would get from each sector. So what are actually the 2 or 3 yarns or fibers I would be working with? And then that might help me. What are the responses? So currently I've been working a bit with living algae, a bit with hydrogels, how they respond to moisture. And hopefully from that, I should be able to say, this is my tolerance based on this material and this is what it can do. But because of currently the amount of programmability that goes even into knitting itself and understanding that and getting up to that level, it has been quite challenging. And I really try to find my way on which would be the kind of criteria, as you just said, that in the end I would say, okay, this is a successful or not successful, or this is the tolerance that I want to have into that piece of prototype. And yeah.
Thank you.
Thanks, Nicoletta, and Tadeja as well. Zaki, please, from CAAD. We are not hearing you, Zaki.
Sorry. Thank you, Nicoletta. Your research really grabbed my attention, especially the future challenges that needs to be addressed in this area. It definitely has a complex and interesting encounter with the interdisciplinary research nature involving multiple sciences. That's very challenging. Really, my question kind of overlaps with the previous panelists, so I think you addressed it at some point, especially when it comes to the buildability or constructability of your prototype. There are different construction layers that, for example, require different structure elements around the mass and density ratio. So I think at this early phase of your research, it's nice to consider start defining the project prototype. Are you going to do a prototype which is a 1 meter by 1 meter, 5? Whenever you start zooming into this, especially to address its application in a real life built environment, you will start encountering additional layers of and the additional pieces. It's not as a subject matter expert, but I think from constructability point of view, you need to look at this. And I do have a question. Users appreciate that computers are great in crunching numbers and doing a lot of simulations, but human designers still need to make a final decision. So how will your research tackle the adaptation of such digital design approach from a user perspective, and how much are you going to join those two worlds between research and the community of designers? Just share your thoughts on that.
So actually, I think I obviously aim for them to work in parallel in a way, but I always, even from the very initial simulations that I had, I can see that especially knitting, and also if you're talking about materials that you program, in the end they would go and you have that tolerance that you really cannot control. So I was aiming that the simulations or the part of the design simulation would be more of a guide initially, and not a kind of a strict thing that, okay, I have that and I want this to match 100% what I have in reality. And it again goes back to identifying that kind of tolerance that I can have from working in parallel with understanding how the fabrication works and the material programmability and how that feeds into the simulation. And actually something that I haven't mentioned that it's very much along my interest, and one of the reasons that I'm very excited with knitting is that you really have, once you have a knitting structure, it's quite adaptable, it's quite pliable, and it is something that could give potentially to the user the ability to adapt in parts the structure itself if they want it. Obviously that's very big what I'm saying, but it is that pliability and that relationship of the material with that kind of surface that can start from being something quite simple from a sheet, but then you can start having quite complex kind of 3D knitted together structures that then might start become quite more structural depending on the material properties.
And it needs more different input, digital input, and there's some constraints to that.
Yeah.
Have you thought of focusing on specific knitting patterns? There's tens and tens of different.
There is tens and tens.
Which one to choose? Which one win the best trophy in self-supporting?
I think currently, initially, I've been started with plain patterns, but I think I definitely want to identify 2 or 3 and do some tests and see which ones are more appropriate for different. So one pattern might be appropriate to have more compression or more stress, and then another one might be better for something else. So I think that is part of the process of identifying the correct bit in each part.
It's really interesting work. Thank you. There's definitely lack of tools for designers to, you know, explore this potential tensegrity of surfaces and geometries. I'm not an expert in the CNC machining and knitting software, but we are really in the baby phases of such world. So thank you for such addressing this area. Good luck. It's really
Thanks.
Thanks, Zaki. As we have some more minutes for Nicoletta, I want to remind the audience about the voting at the end of the session. It's important you stay there and you choose the best presentation for you. And Nicoletta, I have one question that is, you are really working in a very relevant field for architecture and design. And when we say, for example, architecture as an organism, we could think about a metaphor in one side, and in the very other side of really a behavior, you know, architecture as an organism. From your point of view, from your work, what do you think that is the biggest challenge in the simulation about this behavior, architecture as organism, as a behavior?
So the how to translate kind of very accurately the behavior of the material within the simulation.
Yes.
I think in my specific case and looking at the kind of knitting simulation, it is quite challenging because it's very complex. So because if it's not a flat surface that you can kind of align different properties, it's loops, and I think in order to do something very accurate, it would be very, very challenging. The very simple way I've initially tackled it or looking at it is through a very simple simulation from Kangaroo, in which I assign different spring strengths or shrinkage rates within the strings, and then I can apply and then I can kind of test the behavior. And there are actually these softwares are more about translating the knitting pattern onto a form. But it would be interesting to have like a small study of what is that kind of relationship and that kind of accuracy that you can get to. I think it's for me personally, because I cannot say I'm like a high-end coder, or at least now, I think it would be challenging to have like a precise, accurate, unless I concentrated only on that. I think if that was my only part of the process, then I think maybe it would have given an extra step onto the accuracy.
Okay, thanks. And we have one more question for you that comes from YouTube. Can you clarify which simulation tool that could be used for this 4D knitting behavior?
The one I've been doing was Kangaroo. So I used Kangaroo to simulate the string system. There is one that is within Grasshopper. It's called FlexHopper, I think, as well, that looks at, again, you can simulate fabrics and the shrinkage rates if you wish. And then there is another new plugin that is called, I think, Cockatoo. And it gets, this plugin is more about translating a 3D geometry, a NURBS geometry, to a knitting pattern. And actually, I think that's the plugin that came out of the Knit Candela project. That is part of their process of how they translated the quite complex geometry to a printable, to a knitted pattern. I think these are the three that I would be looking at, or the things I've been looking at so far.
Okay, thanks.
Can
And
I ask, could I ask a question? Jane, sorry.
Please.
Jane Scott here from Arcadia. Great presentation, Nicoletta. And I'm going to admit that I come from a knit background, so I have hundreds of questions I could ask. I guess the thing I'm quite interested in picking up on, though, is something you said about how you wanted the material to remain flexible and adaptable and kind of be, I guess, more closely related to what it is than the applications you quite often see in architecture, which is, you know, a material system under great tension. And I wondered if you could pick up on that a little bit and talk about how that relates to your ideas about 4D knitting.
I think in my imaginary ideal world, I would want to have 2 or 3 different fibers or different yarns that would create a pattern. So within that pattern, you would have a yarn or a fiber or something that is a bit more set, a bit more, I wouldn't say structural at this point, because I think that would be an overstatement. But then I want within the other part of the fabric to have the allowance of a sort of a pliability that you could either be able, the user either might be able to adjust it, or for instance, if we're talking about moisture or another pre-programmed stimuli, then that would be the kind of actuating part of the structure or the pliability. So you can use that kind of stretch and push it.
Yeah, that's really interesting. So actually, if you're thinking about, you really are looking across that knit hierarchy, you want to functionalize at the fiber level, but also at the structural level.
Exactly. Yeah.
I guess when I was looking at kind of similar topics, I found that actually trying to cross those hierarchical boundaries within the context of a PhD, firstly, it was absolutely the moment of getting something completely novel and exciting, but also there are just a lot of variables. So I think you're absolutely right that in order to make progress, you probably need to kind of at least have a starting point to commit to some materials and some knitting patterns, just to kind of start creating these behaviors or characterizing these behaviors.
Absolutely. I think that's where I'm currently struggling, or trying to set what are these parameters, because as you very well know, there's so many.
I think it's really exciting, though. I think it's a nice, a different approach, because the other thing I think is great about knit architecture is actually we've now got this lovely field of literature that we can draw from, and actually quite a lot of those kind of initial questions, there is now some kind of theory to base on. So actually, I think there's interesting material to draw from as well. Well done.
Yeah. Thank you very much.
Thanks, Nicoletta and Jane. We will move on to the last presenter, that is Islam Salem from the Ain Shams University. The work is utilizing robotic material deposition and multi-point forming in optimization of double curved facets.
Hello, can you hear me?
Hello. Yeah.
Hello, I'm excited to be here. Hello, Nastia.
Hey, Islam, really
I'm gonna share my screen. Really glad to see you after 10 years. Okay. I'm Islam Ibrahim Salem. I'm an architect and PhD candidate at Ain Shams University in Cairo. My research is about utilizing robotic material deposition and multi-point forming in optimization of double curved facade panels. The technological advancements in the field of digital design and fabrication are still short in providing accurate and cost-effective solutions for the production of double curved facade panels. There are many fabrication techniques available, such as stretch bending or die forming or casting, hydroforming, explosive forming, and multi-point forming. However, none of these fabrication techniques solely were able to accurately fabricate a double curved panel. Only hybrid methods combining two processes together were successful, like the multi-point stretch forming by Lee and Kim in 2012. Also, the challenge with double curved panels is the constant need for mold fabrication. Variations in panel design requires variation in mold fabrication, which consumes a considerable amount of time, money, leaving a lot of waste. Another problem with these methods is the surface continuity, as we can see on the picture on the left, or the bad bending of panels, like the ones in the Mercedes-Benz Museum. Also, a complex panel design that contains protrusions, openings, is not achievable using the traditional methods. My aim is to generate a novel model for the manufacturing of mass-customized complex double-curved panels using a hybrid technique of multi-point forming and robotic material deposition to minimize waste resources and maximize fabrication accuracy. In order to, for the research to realize the previous aim, I need to determine the current shortcomings in the design and implementation of freeform envelopes, identify the parameters of designing and implementation of freeform envelopes, learn about the classification and potentials of robotic material deposition in the construction industry, develop a model for optimized workflow in the design and fabrication of double curved panels, validate the model empirically, and conclude to the method of fabricating the freeform facade panels. My methodology is planned. It is planned to conclude to fulfilling all required construction details, along with keeping the aesthetic and economic necessities fulfilled. The physical prototype is then fabricated using the proposed hybrid method. Optimization of the double curved panel. This is the four main stages that I imagine working on. Optimization of the double curved panels. Extraction of data from the optimized model to be able to set up the flexible mold and extract the tool path for the material deposition. The mold is then automatically adjusted based on the optimized digital model, and the material deposition normal to the mold after making sure the surface tolerance and variation are accepted. That's an overview of the proposed fabrication workflow. On the left is I designed just a little bit complicated double curved surface. And I extracted all the panels out of these design for fabrication preparation. And then we are in the phase of prototyping this multi-point forming machine. We made 5x5 3D printed actuators, which is like the multi-point forming, and we added on top of it a silicone sheet to interpolate the surface curvature. And then we generate the tool path from the digital model, normal to the underlying base surface, and the robotic arm will deposit the material over the modular system. And that's like a simulation of the process. That's a multi-point forming machine by a company called ADAPA. We are really looking into creating an interesting machine like it.
I'm sorry.
Yeah, I'm just wrapping up. I'm finishing in
okay.
just less than 5 seconds.
Okay, thanks.
That's the robotic workflow, the simulation. Last thing is that the outcome of the experiment is measured in terms of material consumption, waste, time of implementation, precision, panel cost, and we can also introduce opening protrusions in the fabricated panel. Thank you.
Thanks a lot, Islam.
Thank you.
Dorit Aviv is the first panelist to talk with you. Please, Dorit.
Okay.
I really appreciate your work, and you know, this solution makes so much sense in a way to work with the additive fabrication method for double curved and rely on a mold like you're doing. But I guess I'm curious about two things. One is you actually mentioned in your complete video that your tests are going to be done with plastic and clay. But I'm guessing that's not the material that is, this is a prototype rather than a facade panel, right? Because the facade panel would have to be from a metal or a material that actually can perform at that scale. I guess this brings into question, you know, the mechanical structural properties of a plate, a metal plate that is formed this way versus a metal plate that is wrought by, you know, point forming over a mold. So yeah, that's my first question.
Okay, yeah, we've been talking a lot about the material. That's why we kept it material deposition, and we didn't decide actually what the material is, as we are experimenting with recycled plastic printing. So this is one of the key to solve plastic recycling, so we can use it. I know it's gonna have that professional look of a metal cladding, but still, if the underlying surface is smooth, it can give a shiny look to the deposited material. Also, clay has environmental aspects, and when you burn the clay, it has like it becomes a little bit rigid, and it can give a lot of environmental. It can actually increase or make improve the environmental aspects of the building skin. So we are experimenting. We can also experiment with concrete, but concrete needs a lot of reinforcement, and we're still not sure about how it will behave. But we are planning to experiment with a lot of materials. Yeah, I hope I answered.
Yeah, so yeah, I guess I'm just going to follow up on your answer and ask, well, clay, you know, it's really a matter. I'm not sure what the thickness of the plate that you're producing is, because clay also would crack without reinforcement if it's very thin, right? So yeah, I'm just guessing. I guess I'm asking. Is the product at scale, right? I mean, it's a question of the thickness, but also the surface area of the plate. I know that there is actually metal deposition techniques now where you can actually do additive manufacturing with metal, but maybe, you know, you're interested in other materials. How do you actually make a shell structure, right? You're essentially, if you're doing clay, you're doing a shell structure. So are you trying to work with like compressive loads to make sure that it is sustained? What is the thickness of it, or are you going to put some layer of reinforcement in it?
Yeah, if we will use clay, definitely we'll use reinforcement fibers in clay or something to give it a little bit more rigidity. And the good thing with the adaptive mold is that we don't need like support structures for it, so we can increase the thickness of the cladding. And this, I mean, the prototype we are working on is not that big, but we are testing for the feasibility of the panel size. So we are planning about 50 by 50 centimeters. That's the prototype we are working on right now. And we will then check the scalability. I mean, we made the actuators modular, so we can increase the 5 by 5 up to like 10 by 10 or something, so we can increase the scale. And we keep experimenting with how rigid and stiff this will actually work. So yeah.
Yeah. So I mean, I think just to maybe close on my questions. The idea of the mold and the robot together and the recyclability of the process I find very strong. You know, I'm guessing that you can remove that upper layer, and basically because it's a die form, you don't even need to throw away most of the form work between experiments. So I think that's a big advantage, right? I mean, that together with the fact that that you have the deposition and you can really work with double curved or freeform surfaces is I think that's really great. I guess I'm interested in the next step once you actually, and I know maybe with the pandemic, everybody's constrained right now in terms of physical experiments, but I'm really interested to see, like, you know, the tests of the produced surface in terms of its structural capacity. Thank you.
Thank you so much.
Oh, David, you're muted.
Sorry. Thanks, Dorothy. Thanks, Islam, and Tadeja, is your time to ask. Tadeja, please.
Yeah, well, what's your next step at this moment?
We are working now on the flexible mold. The synchronization between all the actuators is currently what we are working on. Also, we are working on the robot itself, and we are in the phase of putting on the end effectors, the plastic one and the clay one, as they are both different in size, different in, they require different, I mean, the plastic needs material, an extruder, which is requires we are not using filaments like the 3D printer. We will use like plastic particles. So we need like a big container so we can mix plastic particles and then extrude them. So we are in the preparation of the process itself. I mean, we did some simulations to ensure the feasibility of the project. And we are, the bad thing is that the lab is closed because of the pandemic. So we stopped at a very early stage, and we are not able to use the space or the robot, or so that's why we went through experimentation with simulation.
And how do you see the end of your process? I mean, if there is the end, at least in the PhD, what would be your PhD moment? How do you see it?
I hope I will be able to reach a feasible prototype that can open up the fabrication of the double curved panels. I mean, the potential of having to deposit or to print double curved surfaces, which has been always a problem for, I mean, the architects in their buildings. I have the potential of producing a low waste product, feasible. I think if the prototype is good, plastic is very cheap, clay is very cheap as well. So the prototype will be a very low cost and with no almost no material waste. And I can introduce a lot of I mean, design patterns on our perforations or extrusions that can increase the aesthetic and the quality of the building itself, of the building skin. So I'm hoping to achieve a one-to-one prototype and compare it with an existing building or something, like I said in my proposal, empirically tested against one of the proposals.
Thank you.
Thanks, Tadeja and Islam. We have, Islam, one more question for you that comes from YouTube. It is from Bigun Aktash. It asked for you, he asked for you, can you clarify that you will propose his methodology for in situ construction or a new method of the prefabrication phase?
I didn't get the question well, I'm sure.
Okay, can you clarify that you will propose your methodology for in situ construction or a new method of the prefabrication phase?
I'm not sure I understand the question very well. Can you clarify the proposed methodology of?
That is it's a methodology for in situ, in a real construction, or is a method for prefabrication phase?
Okay.
In an industry.
Yeah, I mean, I know that yeah, I mean, the robotic fabrication will actually work, and I've been working with robots, and I've been working with 3D printing a lot. So I think it will work, yeah. For the prefabrication phase, I think if I understand the question well, I think it works. I think it will work, yeah.
Okay, we have time for one more question to Islam, if we have here from the panelists.
May I?
Okay, Paula, please.
Yeah, hi. Thank you, Islam. I really enjoy your presentation. I have a comment. It's more than a question. So in the past years, Chuck Eastman actually was working on, or actually just thinking about introducing these, let's say, memories from materials into the modeling itself. So you include the behavior of the materials in situ in the model. Let's say gravity affects the materials in somehow bending them. So how do you include the property of the material and the potential bending in situ into the pre-fabrication modeling? And I thought it was a very interesting question, including, you know, tolerances and all the deformations you have on site. So I just wanted to make that comment for you to think about it.
Okay, thank you. I will surely think about that. Thank you.
Okay, I will give the word to Birgo to conduct the last part of the session. Please,
okay,
Birgo.
sure. So we have left almost 20 minutes for our last discussion of today sessions. So if anybody wants to take the lead to start the discussion, you're welcome.
Before the discussion, I would like to address, we have voting for the 5 presenters. And
yes,
it is a voting including all the YouTube audience and the panelists and the other PhD students here. I am now giving you the link. We will just give a brief 2 minutes for everyone to click and pick their choices. I am also putting this also in the YouTube channel as well, and I'm sharing the screen for who would like to see the link. Is everyone seeing my screen? Either you may go to menti.com and enter this code, or you can click on the link I sent to YouTube or Zoom chat. Then you can pick your choice in a ranking way. Yes, I think that will be enough time for all of us.
Thank you, Koray.
Vote. Yeah, thank you. Goodbye.
So let's open up the table for discussion. Actually, we have very interesting presentation about material research in architecture. So if anybody wants to take a lead, I will give the words. If don't, I will ask a question, start this discussion with asking maybe a question. Dorit, a bit.
Yeah, I can ask maybe a question that is for all the presenters today. which is something that, because you're all dealing with maybe except for Natalia, everybody's dealing with material properties, right? But also including Natalia and everybody else's presentation, simulation and validation or prototyping seems to be, a very, it is a feedback loop, right? Between simulating the material behavior and then trying to prototype it and then going back into the simulation, adjusting the model. And I guess during this pandemic, like Islam mentioned, a lot of labs are closed and you have to rely more on simulation. So yeah, my question is, what are the challenges in this cycle and how are you developing new tools to deal with the fact that you have less kind of hands-on research at the
moment? If I may jump in, as I say, you're absolutely right. The issues with not being able to access a lab and work effectively with a material is a big thing at the minute, and having to work a lot on what we know already about the materials, and especially in my situation, I'm having to go off a very limited amount of knowledge which I was able to gather prior to the lab shutting between sort of January and February. And then working with sort of simulations and stuff over the summer when we've been in lockdown, and now we're coming out to the other end, we're actually able to get back in the lab and test these things, and it's been quite nice to see the relationship between what I expected and what I'm actually getting. I found it really informative. There's been certain materials which I thought would work really well with my spores, which actually don't, and there's been some which I thought wouldn't and actually have, and I think it's really helped me to rationalize what properties I actually am working with instead of what I'm expecting to work with. So what levels of but it makes me identify those properties quite clearly. And I think simulations as such are fantastic to give you an overview, but I don't think they can actually compare to being there in person.
I can jump in as well. I think in my case, my kitchen became a lab a bit, and because it's and it was actually quite interesting, and I think it's good to see that some of the parts we can still carry on within that environment, and it doesn't have to be 100% always a lab environment. And it's a question, how do we actually use it? How can we scale it up, and how can we make it more accessible? So I think that's a question that we've all been trying kind of to solve and see with what kind of tools we can use within home or within an environment that are easier to be potentially replicated later on, instead of having high-end machine access to things. So it's challenging, but I think it has benefits as well to the whole process.
If I can add to that, I'm perhaps more fortunate compared to my research peers here working with Earth, which is quite ubiquitous and readily available. In fact, I am not in Cambridge at the moment, but where I am now, I have sort of better climate and better access to Earth samples. So it was kind of better in that sense. But of course, the hindrance was when the pandemic first happened. I mean, the university shut down, obviously, like anywhere else. And then we lost access to the lab and then the access to the clay printer too. So that sort of caused me to lose some precious time in research. But now I made amendments and soon I will have my own clay printer. So I will just catch up with where I left. So that's kind of my point of view. So I think it had kind of ups and downs for me from both point of views. Thanks.
Here, I'm not with material, with physical materials, but this year was really tough. Here in Brazil, we live with a lack of resources to do research. And for me today, I'm far from my university, almost 40,000 kilometers, because we have 4,000 kilometers because Brazil is a really big country. And I'm far from my laboratory, almost a year, and I'm working in my home. I needed to buy a computer to do my research. I postponed my internship in USA. And it was a really tough year, but we need to do research with love, always with love, no? For everybody, but for me, I'm not working with material, with physical material, but the pandemic was a complicated situation.
Yeah, this really not having access to the tools and the environments and the material, it's really broke our research processes. But as you said, we should not be pessimistic and just continue to do whatever we can do in these conditions. Saving life, actually, giving us support for living and bearing with this situation. Actually, I want to ask one question to all you, maybe to open the discussion. When I was doing this kind of research with my students, especially about the materials, what I found is there's a shortcoming of architectural field is that most of us, and Emily a couple of times mentioned in her presentation saying that I'm not biologist and I'm not biologist. So we come up with, and all the research agendas are really great and innovative. But what I found is a something that we are really having trouble to achieving, this innovative material generation applied research, let's say. Like, we generate these ideas in architecture about the materials and about the behavior of the materials, but we are really lacking of this other scientific knowledge about the material, like a biologist or material scientist. So I always find with my students the problem of not having this really joint research project, that the material can come out as a product, for use, for the industry, we come up to one point and then we have to leave there because our knowledge is not in that area explicitly. And we generate very good ideas. So I would just want to ask the panelists and all the PhD students how we can really bridge that, because our strength, we are using the strength of generating ideas. We have very good ideas. We have very good maybe processes, and we come up to one point, especially about the material research in architecture. I'm not speaking about design. Design is our issue. I mean, we are doing a very good research about in this area, but I think we have something to switch into another level with this integrated research to put forward a bit our research agendas.
I'd really like to sort of join in with this, if I may, because I'm in a very lucky position that the group I'm part of, which is the Hub for Built Environment, Technology in the Built Environment, sorry, I'm muddling my words, it is specifically set up to combat this. It's a fantastic collaboration of biologists and architects and designers, and it's a brilliant platform to work for. On that, we have one of my supervisors is a biologist, which is giving me the support in that area, which I don't have a background in. I have an engineer who is another one of my supervisors, and an architect as my third. So it's quite nice to see this as a topic of conversation starting to be discussed, because it's very sort of pivotal to what we're trying to do. And I think multidisciplinary work is vital for pushing these sorts of materials forward, because it needs a multi-pronged approach of different specialists working on their own area of this one thing. I don't think any one person has all the skills to be able to produce something that's going to, change the world as such. And I think, and as an architect, I think it's really important to be, in an old-fashioned sense of the word, an architect, as someone who brings it all together. And I think it's quite an interesting standpoint to work and design from, and not necessarily feeling the need to be a specialist in every area, but trusting your team and trusting people who do know those areas to inform you on how best to go forward. Yeah, I think this is a really exciting future for multidisciplinary work, and especially with biomaterials and things like this.
And perhaps I can add to that. I am also fortunate to be a member of Natural Material Innovation Group in Cambridge. So we are a research group, and we are in close collaboration with engineers and biochemists and plant scientists and material experts. And it's really valuable and necessary to pull that expertise when required, and for idea exchange as well. So it's great to have that brainstorming once in a while, not just for, a specific topic, and come together and discuss some issues. And if I might add to that, I believe also collaboration with industry and architectural practices are very important, not just experts, I think, if we want to realize this research. As an example, for example, the tall timber research project, which was done by our research group in Center for Natural Material Innovation, with funding from Leverhulme and with collaboration with PLP. And that research project, if the regulations allow, might happen perhaps in 5 to 10 years. So just another layer to that. I think it's also important to bring in the industry and practices as much as possible.
Yeah, that's an issue really in architectural schools, that maybe you're lucky to be in interdisciplinary research group, but most architectural schools unfortunately lack these interdisciplinary research groups, and they are trying to do the material work or like design material development, which really requires this kind of setup and environment to have an advanced work and the product coming out actually as a design of the research. Yeah.
I wonder about what is actually happening with the individual research then. How do you see then the different drivers or different moments, because this is not a stable environment? Some mentions, for example, one says this is research by design, but then you are talking about all these drivers, and then the other creative practice research and so on. But here we have two basic drivers. One is design thinking and acting. The other is computation. But then we have bio whatever and materials and so on. So how do you see all these, like orchestrating this? You are the orchestrator, the conductor of this. How do you see yourself as a conductor of this kind of, let's say, design research drivers, but also modes of knowledge that you are combining?
Well, I can maybe start. I think it's again it is very challenging, and it's challenging because up to a point you need to understand up to a specific extent the different disciplines, and it's quite hard to find the line to say, okay, now I know enough and I can turn back and do design. So it's like, what is the point that you say, I've understood enough that material, now I'll go. They kind of work hand in hand, and but I think these are the points that also when you look at things from a different perspective, then something innovative could come up. Someone would tell you something, and then you would think about a fabrication method or about something that you wouldn't have thought otherwise. But you can easily get lost at the same time. Yeah, that was not a specific answer, but it's yeah.
Yeah, I second Nicoletta on that. I think she's absolutely right. It's really easy to get lost in this process. So I try to kind of put my checklist in front of me every day to not to get lost, because it's really easy to get lost. And it is indeed a very empirical process. I think a trial and error is very important, and learning from the errors, hopefully. And yeah, in my mind, I picture it as a very circular process. that like doesn't have like a beginning and end, but it goes kind of in circles, sort of back and forth.
I was lost in my PhD time. Almost all the. For me, I like to draw. I like to draw diagrams for everything. For me, it helps a lot to make a direction and to think. And I like to speak with other people with other backgrounds, other areas, people from the industrial design, from the digital fabrication, because I work with environmental comfort, and sometimes for researchers in this area, digital fabrication, it's a complete different area. I think we need to integrate the design areas, all this knowledge, and I think this is a good recipe to do something that it's innovative or it's good for anything.
Yeah, if I may, I work at a research institute, so for me it's easier to see the connection with the practice and with other areas as well. And I believe that in general, other areas don't know what we do. They kind of have this idea of old-fashioned architect or designer, but when they really learn what we do, they are very willing to collaborate. And in my experience, I think we need like a structure, more like a platform that actually allows that to happen. I have a great experience at Georgia Tech with this vertically integrated project, which is basically like a research class where every student, any student from second year to PhD levels from like across campus, any college can actually register for credit. So it's like this platform, very flexible platform where you can call for a research group in all the areas that you actually need for your research. And the students are actually very willing to contribute. So I really think we need to spread the knowledge, like what we actually do, and actually create a structure that supports this collaboration that we all talk about, but it's very difficult to actually implement.
But I think that's the implementation, because the academia is still in silos. We have to really break first that compared to industry, because the current world doesn't work and function separated silos. But industry functions totally in different manner in collaborating platforms and everything. But academia has more that traditional view of being in silos. As soon as I think we are aware of that and we start breaking the silos, then the things will change. We're still more conservative about our knowledge, our field, but there is no such anything anymore. Everything is just like mixed, and idea and knowledge. Knowledge is in the middle everywhere, but how to use that knowledge in innovative ways, in collaborative ways, I think that's the matter. And as soon as we understand that, we will make a breakthrough, even in architectural research as well, I think. Okay, anything else you want to put on the table for discussion?
One more comment below about the Tadeja's question. I think that the point is the questions that we are making, you know, from design or from architecture, we usually make some questions, and working with in an integrated manner, we work with people that make other questions. In my field of work, we are working with spatial data visualization, and I work with a sociologist and a philosopher, you know, that they make some other questions for me, and then they put me in another place. They shake me up, you know.
Yeah, they make us think differently.
Yeah, yeah.
It is the same for me.
And in many cases, can we say that they push us out of our comfort zone if we are really collaborating with other fields? So we are kind of pushed out our comfort zone from our knowledge of expertise and pushed to think with other classes, probably.
I'd like to assume that if we really collaborate, and I do that a lot, the main problem is actually to get funding, because funding is mostly available in very specific subject areas. So if you collaborate, I think architects and designers, we're very flexible, we are very good at collaborating, but that means that we usually join other people in their fields rather than drawing them into our fields. And that's a big challenge. There is no such thing as a funding category for collaboration. It's assumed you do it. But it's a real issue. I'm speaking specifically for China, where collaboration across discipline is totally not encouraged. I mean, people may say that, but there's not even a category that acknowledges that. So research into specialism is rewarded, but not the other way around.
Actually, it's in our country and in Europe, it's another way around. Like if you have a collaborative work, then you get really funding. If you are immersed in your own field, especially for architectural and design, there's no way that we can get support, research support.
That's good to hear.
Yes, especially in Poland, certain applications for young researchers, like the highest category that you can earn points in is if you're in a collab with either multidisciplinary, international, multinational teams, and that's like basically the top thing that gives you points for possible funding.
So, any other comments or intriguing questions to pose to our audience, or if we have any comments from our YouTube followers, audience? Let's say the chat window, actually. No, I think
the chat window is quite silent right now.
Silent, yeah.
They're watching us in complete focus.
In complete focus.
Virgil, if I may.
Sure, Sharif.
I think, since we're talking about, it's sort of multidisciplinary work and also cross-cultural or multicultural dimension, especially here with the PhD workshop. And echoing what Candy was just mentioning about funding, and also Paula about reaching out. I think this is also a unique opportunity because sometimes you in some continent or some culture have something that somebody else needs in another kind of university or lab that's looking for this certain kind of material that's, for example, only located in this geographical location or something, or whatever kind of collaboration. So there are opportunities, I think, that within what we're discussing in this workshop, and I hope this is brings out the future kind of added value of this network and the start of this series to kind of more maybe it's not really evident in the first kind of version of the workshop, but I think this drives an opportunity for real kind of cross-cultural and cross-continent collaboration, and then hopefully the other step with the multidisciplinary, actually us reaching out as a community, as 5 sectors of that community, but also reaching to the other disciplines in that regard, because we have certain every single kind of region or culture has a specific kind of hidden, latent kind of power there, whatever it is. Some is more like really tech savvy. Another is really rich in heritage and material, for example, and so forth. So there is an opportunity out there that this forum might kind of seek that opportunity or capture it in a way, and sort of grow this network to potentially kind of address other disciplines to speak to that. Because
it's always kind of by chance, for part of my research as well, like working in hygromorphs as well, but also just by chance reaching with other collaborators and then thinking about, okay, what can trigger the, for a hot arid climate like Egypt, how would I work with humidity with wood, for example? So just starting to work with other collaborators in other environments and testing the different kind of impacts of their research and their climates and our climate, and then thinking about, okay, what kind of material would trigger the release of humidity, for example. So I would come across somebody who's working in hydrogels, like Dorit mentioned, and then, okay, so this thing really works with, and it can be triggered by temperature, which we have. Okay, so, these kind of, interesting topics come across, but just by chance, sporadically like that. But I think not so much of a structured framework, but I mean, this forum of cross-continent kind of PhD topics, I think is a wonderful opportunity for expanding that and reaching out to other disciplines in the future.
Okay, I would just pick up when you left. I think this was very good, almost concluding remarks for our 3 days of workshop. I remember, I always said that we should first learn to collaborate within our discipline, then try to seek out for other disciplines. So this is a very good start, I think, as you mentioned, like cross continents and different cultures collaboration, just to meet each other, to recognize each other, to see how our research are developing. And I'm quite sure that the platform, this forum, will produce larger collaborations, wider collaborations in the future. But we have just started meeting, Hadria is meeting CAAD students, as CAAD students. This is the first step. We were not able to do the conferences together for such this years. So this is the first step, and I think it's a wide step. They'll have a very good results. By saying that, we are almost approaching our ending time. I will write on my, in behalf of the old sister organizations, I think President, probably you will take the words as well, for organizing committee of this CAAD workshop. Thank you all the participants or the panelists and all the YouTube followers that are quite excited following us. Personally, I learned a lot through our PhD, presenting PhD students and our discussions through the panelists. Enjoyed this 3-day event, and I'm quite sure I will be following this workshop just to see the bright and the interesting subjects in our CAAD field and how it will develop in the future. So thank you all for joining. And before we close, I will give the word to David to announce the next workshop, the next year workshop. And I will just say that we had 3 days voting, and the results of the 3 days voting will be announced on the website by next week. Of the best presentation award, proposed presentation, yes, for the best presentation of this first workshop. So follow the website. So David, you can announce, and then the next year's workshop.
Okay, thanks, Birgo. I will share my screen with you, and I'm glad to announce the second World CAAD PG workshop that will be held by Federal University of Juiz de Fora, held virtually, okay, and in Brazil, on December 6, 7, and 8 of 2021. And I guess we are starting a tradition that we will close each year together in a PhD workshop. We welcome you to join this PhD, and we will very soon spread the word about the dates, the deadlines. And we, in the next year, we will have another way of selection, a joint system of selection that we will very soon give to you the news, okay? And I, from behalf of SIGRADI, I want to thank all of you for your work, for your endurance, especially Birgul that came to the front this year, organizing everything, and the other presidents too. I'm very proud about this joint work that we did this year in this pandemic contest. And I wish you best of the best at the end of the year, the next year, and thank you for all. Yeah.
Thank you. If we have another two presidents present here, if you would like to take a word, Candy, Sharif, the last words, and then we will just make a good applause of today's presenters.
Thanks, Birgul, and thanks also, David, and basically thanks everyone. Thanks for the courageous presenters, and thanks for all the panelists who made time. The silver lining that Katie was talking about in the very first introduction on Monday is really what is the takeaway of this conference. We have a pandemic, but because of that, we all went online and we are coming together like we would never otherwise come together, and that's something great. And I'm very happy to see the next workshop already announced. Thanks, David, for taking it on, and we'll now circulate it. And I'm very much looking forward to that. And so I think, Birgul, thanks for doing all the tremendous work, getting us up to this level. And now we have a template to work from, and we can steadily improve it. And so thanks to everyone. It's been a real pleasure to see everybody present and to see all the great work.
Thank you.
Yeah, it was a great experience, and I love the news about the next workshop.
It's fantastic. Thank you so much.
Thank you all.
Thank you all. It was great.
All the experience was really, really great.
Thank you
Thanks
to
again
all.
for everything.
So hope to meet. Sharif, do you have?
Yeah, sure. Well, thank you, Birgul, first of all, and Koray and the whole team behind this. I'm sure there's a whole bigger team also in the background that we didn't get to meet, but I know there's a lot of people working on this. And you have successfully raised the bar for next versions of the workshop. So looking forward to those as well. And I personally it was a great learning experience, as you mentioned, for all of us. I think enjoying this, living in this 3-day kind of bubble, you know, very, very nice dream come true. And also, you know, literally getting exposed to leading research across the world. So it was really a fantastic opportunity and very, very rewarding to sit in all of these 3 days and listen to the fantastic research everybody's doing. I think everybody is doing fantastic work, and they really need big round of applause, literally, and really looking forward to this workshop series to continue forever. I think it's setting a very interesting and hopefully very fruitful example for us. Thank you.
Okay, thank you very much. I would like to, as I said at the beginning as well, the opening session, that we were not alone, Koray and me. We had a team of this PhD students from our graduate program at Istanbul Technical University, Computing in Architecture. It was a great support of the students, and I'm quite sure that all of them are now following to the YouTube because they were so excited to see. So thank you all again for joining, and hope to see and meet with you next year for the workshop, for the second round WordCAD PhD workshop. Have a nice holidays and stay healthy.
Thank you so much.
Thank you. Bye-bye.
Thank you, everyone.
Thank you.
Bye.
Thank you. Bye.